Good morning. Welcome back on the Milliways stage for the second talk on day 3. And we welcome here our speaker Garrigan, and he will talk about demystifying Mach-O. Please give him a warm welcome and enjoy the talk.
Howdy. Everyone can hear me? Cool. So let's start with just who I am. I am Garrigan. I work on an iOS cybersecurity framework over in the States, and this isn't too important though. Let's talk about what we're going to talk about. So first we're going to look at what is Mach-O and why you should maybe look at it if you want to. Then we're going to go into the deep dive into the file format and like the specification for it, and then end with a little code example about how you could parse a Mach-O file to get some information from it. So first, Mach-O is the executable file format for Darwin systems. Think iOS, macOS, tvOS, all of those systems. It's very similar to ELF, if you've ever used that for Linux, but it's a bit different. It's an architecture-independent file format, and essentially any iOS app or a macOS app that you create or want to reverse engineer or look at will end up as this file format, generally speaking, on the device or on your machine. So there's a few reasons why you might want to look at these files. First is if you want to read executables at runtime, such as doing metaprogramming on your own code, or if you want to do integrity checks on your own code, or maybe you want to do something like Frida and install trampolines on other people's code, and that requires, being able to parse through these kind of files. Custom build tooling, so if you want to inject data into your executables in specific parts of the segment, so that you can have like the loader automatically map data really quickly for you, or you can have special hashes for integrity checks inside your executable files. Any disassembly or reverse engineering, you're going to have to look at these things. Like for example, you want to see what Apple code looks like. A really good way to do that is to load one of these files by linking the dialib into memory, and then just dumping this executable file and disassembling it yourself, so you can see what's under the hood for these types of system libraries that Apple usually hides pretty well. So yeah, those are various reasons why you might want to look at these files and how you would get to them. So it's a binary format, so as we go through, we're going to fill in just this block of bytes to show what the structure of the file looks like and how you might get to various parts of it. So first, we have to talk about what are called fat binaries. So fat binaries are essentially a way to contain multiple executables of different architectures in the same file. So essentially you have like a program and you want it to have x86 and ARM64 instructions on it, so you can run it, or maybe 32-bit and 64-bit applications on the same space. You can just put them right next to each other. And once it's loaded, it only actually loads the architecture for the current machine, so the loader will know not to pick up the entire file, but only the one for the current machine you're on. And you can have a fat binary that is only one architecture, but the existence of the fat header is very optional. It's not required, but it is possible for it to be there, even if there's only one architecture. It is important to note that these are kind of going away. Fat binaries were used for a very long time. You still use them on applications you find on the internet for Mac, but most iOS applications do not use fat binaries anymore because there was a conflict in the iOS 16 ARM64 simulator that made it so that they couldn't, essentially there was a naming conflict, so they had to reintroduce XC frameworks, which are essentially a better version of this. But yeah, this is a way that you can have one file represent multiple architectures and not have to worry about like giving people the x86 or the ARM64 version. So a fat binary starts with a fat header. You can define these definitions. I'll list the headers as we go along. They're all in the system headers for iOS and macOS and all that. If the file is a fat binary, it'll start with a fat header, and you check that by looking at the magic number there. It gives you both fat magic and fat cygam, so you can determine the Indianness of the data that you're about to look at. That's very important for the fat header because it may be produced on a machine completely different. Like, if, for example, you could be reading this on iOS, but it was produced on an x86 64 Intel machine, like a Mac. And so you use that to determine India, so you can actually read the header correctly. It then tells you the type of the header tells you how many architectures there are. Each architecture tells you the CPU type and subtype that it belongs to, as well as the offset into the file that architecture belongs. And then it also tells you the size and the alignment. The size will always be an integer multiple of the underlying page size of that architecture, right? So I think for ARM64 that's 512 bytes, or yeah, I think so. Yeah, and then of course it's a 64-bit variant. There's also APIs you can use in machine.h to determine which CPU type belongs on either your machine, or if you want to try and like grade. It's the same thing that all operating system uses to choose which architecture to load, but it'll grade slices and then determine which one to load. They have those available in machine.h. So if you're like opening a framework up on disk and you want to check which one to use, you can use those to make sure you're loading the correct one, or at least looking at the correct one. You can use LiPo and OTool. These are two little command line utilities that come in the box, and you can use them to kind of see fat headers, and also LiPo lets you inject or remove various slices into a universal or fat binary. You can see here, we can see the header and all the type of stuff within it. So yeah, so this is the structure at this point. We have a fat header, two fat architectures, let's say this is 32-bit, 64-bit, and then we have two Mach-O objects which define executables at the same time. Theoretically, these are two programs, just different architecture. Same program, two architectures. So a Mach-O object is then kind of the way that if you're familiar with how like segmentation originally worked in memory for operating systems, it's kind of this influences how this works here. The object is split into segments, which are effectively memory ranges that will exist in virtual memory when your program is running. Each of those have their own memory protections and a space that the loader will then map into your process's virtual memory space. They all begin with the header, and they are followed by a list of load commands. The load commands define everything else about the file, so once you read through the load commands, you know where everything is. Each segment can have, sections inside of it so that you can have a little more information on where things are. And we'll go through the definition of a lot of these going through. We're not going to look at every segment in every section because technically there's you can make your own segments and your own sections. There's also just a lot of them. So you can use OTool to look through these on various files that you already have. And yeah, so if we look at some common segments, so these probably should be familiar. Page 0 is a null pointer trap. On Mac, I know different OSs handle it a little differently, but on Darwin, they actually don't map page 0. They just claim it to have no protections at all, which that gives you your nice behavior where if you try to dereference a null pointer, it crashes instead of just doing whatever. And so there might be a change to this. I remember reading somewhere that they were looking at actually mapping it, not allocating memory for it, just mapping it, because apparently there's a null pointer exploit because of the fact that it's not actually mapped. And for 64-bit applications, this doesn't just map the first page of the process space. It also maps all of 32-bit application space. So on 64-bit apps on Darwin, you cannot dereference a 32-bit pointer. And it also means that you can't load a 32-bit library into 64-bit space. So that's a neat little thing they did there. The text segment is usually the first segment. It is the first segment, and it always contains the mock header. The reason it does that is so that when you're code signing your stuff, the code signing only looks at the text segment. So whenever you have signed executables from the iOS App Store or whatever, it's just looking at that first text segment. That's the only thing in the executable that gets code signed. That also means that if you have data that you want to be code signed and have integrity protection on it from Apple systems, you can put it in the text segment. You can either via a C string, or you can actually just explicitly tell the compiler, hey, put this in the text segment. Watch out though, it means it'll also be executable, so I don't know, take your risk there. Data, that's where all your common data, immutable state will be. Data const is a bit interesting. So yeah, the way these protections work is left is the initial protection, so you can see on text it's read execute, and then right is max protections. So that's what you can theoretically upgrade the segment too. So like on Mac, you can make your text segment writable. Data const is a bit weird. So data const, it was a section that was added because originally there was no const data on Darwin or any Mac system like that. They just had like a section in data that was assumed const for like the global offset table. That isn't great because you can just go in and, like, for example, an attacker can go in and change the global offset table, and then suddenly all your calls to any system functions can be easily detoured. They kind of fix this by adding data const, which is also not const, but instead what happens is it starts out as read-write, then DYLD, after it's done dynamic linking, will make it read-only, but you can always just go back and make it writable again because it has the max protections and DYLD is in user space. So it's not const, but it's by default though const. However, there is a change happening here. In iOS 17, they are releasing, which I should be releasing in like a month or two, they added this SG read-only flag. So this flag, when added to a Mach header, will have the kernel make it actually read-only after DLLD is done. If you don't want that behavior for your executable, you can remove the flag, but that's something you notice. So maybe if you're trying to hook another executable, look for that flag because it might break all your hooks. But that it will actually be const or closer to const in iOS 17. And then there you have things like your global offset table, your Obj-C class list, and const data, that kind of stuff. And then link edit is at the end of most executables, and it's just linker data. It's where DLLD will get its operation codes because DLLD has its own special op codes that are used to define how to update the various dynamic linking in the file. So let's look at what an actual Mach header looks like. First, you have the magic number to make sure it is correct. Like similarly, it has an Indianness check in it, so you can check if it's MH magic or MH cygam. And it again contains the architecture info, the file type. We'll look at those in just a second. It also contains the number of load commands and the size of the entire list of commands, and that's because load commands are a variable size, which we'll get into in a bit. That has some annoying implications, but yeah. And then it also has some flags on it. That's where that SG read-only thing, this is where this would be. There's a lot of flags, and they're mostly used by the linker, but here are some ones that you'll probably see if you poke around. No undefs means that it's fully linked and doesn't need to be dynamically linked. Pi, every executable should have pi. That means position independent. Don't write position dependent executables. That's really not great. Has Obj-C just means it has Obj-C. DYLD means use DYLD. And two-level is a feature where DYLD will create namespaces for the libraries that you link against so that there's not naming collisions between symbols. I think that's on by default, but don't quote me. Here are the various file types that are known. Presumably, Apple might have some more that they just don't publicly define. Object, that's like when you compile a C file. It's an intermediate object representation of machine code. Execute is just an executable. FVM lib is an obsolete VM file for like in the old days. Core is for when you get core dumps. So if you ever want to investigate core dumps, those are also Mach-O files. That's how like Apple gets those crash reports on them. Preload is also an obsolete one. Dylib is how you determine a dynamic library that wants to be loaded. These have to be loaded. So like think libobjective-c.dylib or whatever. Those are all dylib files, dylib executables. They can only be loaded via load commands inside another executable or through an explicit call to DL open inside a running process. Dylinker is a special executable file that is a dynamic linker. You can make your own and have executable programs point to a unique dynamic linker if you don't want to use DYLD for whatever reason. MH bundle, that one is for resource bundles. Those actually can only be opened via bundle APIs in code. You can't open them via the loader directly. DSIM is for DSIM files. And Dylib stub, that one's an old one. It's not really used anymore. Essentially, Apple doesn't want to give out its source code in Xcode. So the way they do that, they used to do that was to create empty executable files that just had symbol tables. So you could say like, oh yes, link me to this dilib, and then on Mac, on your development machine, it would have no code, but it would link correctly, and then on the phone, it would work. They've replaced that with this new text-based definition file, which we won't get into, so you probably won't see that around. If you wanted to try and poke around Xcode to see what APIs are available, you'll see a lot of these text-based definition files and some of these dilib stubs, which are just essentially just empty files and lists of names. And yeah, and then kex bundles for macOS kernel extensions. So yes, this is kind of what we're looking at now. Each individual object has these load commands, and we know that there's segments somewhere spread about, but we don't know where they are yet, and we don't know how big they are, and we don't know what kind of memory protections they have. But we can figure that out by looking at, but we do know where these load commands are, and that's where we're going to find out all this extra information. So a load command defines the various segments and sections, and also other various things such as OS version and name and all types of stuff. There's a lot of load commands. They are of variable size. As you can see, the base load command is just a type and a size. That also means that you can't index into load commands. You have to go one by one and look at each individual load command as you go through. So whenever you're parsing one of these things, try and make it to where you only have to do it once, so you don't have to do an n-squared algorithm of going over and over again. And we're going to look at a few load commands, but they're all very different. There are about 47, I think, load commands currently supported, or at least publicly supported by Apple on Darwin systems. However, you could make your own, and you could also presumably if you make your own dynamic linker, you could also use them somehow. So we'll look at a few common ones, but if you want an exhaustive list, I think loader.h has most of them, and you could also look at Jonathan Levin has a good list that's pretty exhaustive of which ones are actually used. So first look at probably one of the more important ones, which is the segment command. There's 64-bit versions of a lot of these commands, which is _64. You'll see this pattern a lot when looking at load commands, where it's basically just C-style inheritance, where you have it's the same as the load command in the first two fields, and then just adds a bunch of stuff. So first it starts with the segment name, which is a 16-byte string. That's where you get things like text, data, data const. So that's where you'll be looking for those things if you're looking for a specific segment. Then you get the address and size in memory. Note that if you're reading from file, these are 0, or at least I wouldn't trust the values if you find them here. These are provided by the loader as it loads it into process space. So if you're reading it off a file, this will probably be 0 or maybe some other garbage value. And if you're reading it off a file, you're going to want to use file offset and file size. That tells you where in the file and how big it is. I also think there might be a potential difference between file size and VM size, as I think VM size will always be page aligned. Well, I don't know if file size is guaranteed to be that. Then you have your maximum and initial memory protections. And then, of course, you have something called sections. So each segment is allowed to define sections within itself. The sections are more logical than necessarily physical, but they are there to help define and separate the segment into logical sections. If the insex flag is greater than 0, then that's how you know there will be that many sections immediately after this segment command. So there could be, it's immediately after the command. It's not located somewhere else. It's just right after it. And that's where you get these section commands. A section has a 16-byte name as well. And also you can see it has the address that it's currently located at, the size of bytes in the section, as well as the offset. Similarly, address may not be filled if you're reading it from disk. Use offset. The alignment, the relocation entries, all that like kind of symbol stuff. The flags are pretty interesting, but essentially the 8 LSB determines the type. So for example, you could have a section of C-string literals. This is very helpful when you're trying to parse because it tells you how to actually interpret the section. So like a C-string literal section is literally a list of null terminated C-strings. So when you know where that section is, you can just build an array of strings pretty easily off of it. There's various types. You can find them in loader.h. The other bits are used for various attributes, such as you could say it's a debug section, which means it has debug symbols included inside it. And also, sections are naive in that there is no checking to make sure sections make sense. You can have the bounds of a section are not guaranteed to overlap or not overlap with any other section. They're not guaranteed to actually be ordered. There's no checking. It's just off of good faith. So there might be an exploit there. I don't know. Maybe y'all can think of it. But there is no checking there. You can probably come up with some things to fuck with sections, or at least fuck with your disassembler. You can also create custom sections inside a segment. By using in code, you can just say this attribute like, put this section in this segment. This is also how if you wanted to put data in your text segment, you could create a custom section, put the data in there, and then it'll get code signed. And then you can also create a section via a file by using this linker command to LD. Another load command would be lc main. This literally just tells us where the main function is. So if you're ever interested in where the entry point, finding entry points can be kind of hard in code. Luckily for executables, you just look at this guy. It'll tell you exactly where it is. Another one is die-linker. This actually specifies the dynamic linker that the operating system should use when fixing up the executable at runtime. Usually it's DYLD or DYLD_simulator if you're working on simulator. But you can always make your own. I don't know why you would, but you can. And you can always just have your executable, or what executable you're investigating. You can always overwrite this load command with your dynamic linker, and then you're able to then capture and get the fix-ups. Maybe you want to see what symbols various objects want to look at, or something like that. And then this is probably the other more common command you'll see is the load command. This is what loads dynamic libraries into your process space. It uses this dilib struct inside of it, which is this long thing of various... it's just like a bunch of data structs inside of each other. It's just nested for you. And it has a command, and command size just tells you where it is. There's various versions of this one for all the types you can import a dynamic library, such as weekly or re-exporting and all those things. So this is the basic structure of a Mach-O file. You have a fat header with various architectures after it. Each of those architectures has a Mach-O object that has a header themselves, followed by a list of load commands inside of the text segment, and those load commands tell you where all of these segments lie within the object, and then you can use the various things to go through and look at the sections and look at the various load commands as well. So to give this a little more concrete example, I wrote up a little program that will extract the Obj-C class hierarchy from any process, any memory, any module loaded into process space, and we'll just go run through that so you can see what it looks like. We're assuming 64-bit because I don't think Apple supports 32-bit since like 2017, 2018, and also I removed some error checking to make sure that it's not too verbose. So we're gonna look at all of all the system modules loaded into just a basic Hello World application, and we're gonna take a look at what their Obj-C class hierarchy is by just looking at the executable images that were loaded by the system. And for reference, Obj-C only has single inheritance, and the root object is NS object. So here's our main function. This first bit here is just some way so that it didn't take forever. It's just parallelizing it, so don't worry about it. The first important bit is that we do want to see every mock image loaded into our process, and we do that with DYLD register func for add image. What this will do is when we first call it, it will use this callback we give it and call it for every single image that has been loaded as of yet into the process. That includes our own image as well. Then after it is done doing that, it will go to sleep, and then anytime a new image is loaded into the process in the future, it will also call into our callback to let us know this happened. So if you ever want to monitor what images are being loaded in and out of your process, this is a really good way to do that. Maybe you're worried about someone injecting themselves in there or something like that. But this is a good way to do that, is to use this DYLD API. So in our callback, this is what the callback signature looks like. It gives us a mock header and the slide. The slide is referring to address layout space randomization. Essentially, whenever the OS loads you into memory, it chooses a random place to just plop you so that it's harder to determine where your code will be, so that things like stack overflows and buffer overflows are less exploitable. Note that the mock header here is technically a 32-bit one. I don't know why they did the API like this, but it only gives you a 32-bit one. But luckily, you can just cast it to 64-bit and it works fine. Actually, you kind of have to. Yeah, so next we will just go into here. We're not going to look at the export hierarchy code because it's boring. So we'll just go straight into the actual Mach-O parsing. So at the beginning here, we're just doing normal Objective-C initialization stuff. And this is where you can see I'm just casting it to the 64-bit mock header. You just have to remember to do that. If you're doing things in production, you would probably, have a preprocessor defined to make sure you're choosing the correct headers here. That's actually pretty common, is just redefine all of Apple's structs to be based off of preprocessor definitions, so that you always get the 64-bit or 32-bit version. Here we're checking that file type. We only care about dilibs. We're not going to look at bundles or executables or anything like that. Note that we don't need to actually check for Indianness because it's loaded into our process space, and so hopefully it's the same Indianness as our process. And also we're not looking at the fat header because it's also loaded into our process space, so we don't need to know which architecture we're looking at. Once again, to reiterate, if you are looking at fat headers, you do need to check that, and if you're looking at architectures that you're unsure of, you really should check it so that you can swap. Yeah, and then we go to parse the binary. So this is kind of the basic iteration loop of parsing the binary. First, we grab the load command, which is right after the mock header. So we just take the next element after that and cast it. Then, as we iterate, we just double check that our current command as a byte location is less than our size of commands. And then starting at the beginning of the first load command, and then to iterate at the bottom, we just add the command size from each particular command. Yeah, and then at the end we return nil if we return true if we parsed it correctly and all that stuff. So here's the inside of the loop. You see this, you'll almost definitely use a switch structure just because it's convenient, because you're going to be checking IDs of load commands, so it makes sense. So in this first case, we're going to see if it's a dilib, and if it is a dilib, we're just going to grab its name, or this grabs the name of the dilib that was loaded. So this lets us, keep track of which which images are which. Here we're grabbing the segments of that image and trying to see which one. If it's a data cont section, then we move on because that's where the Objective-C class list is. We then iterate through all the sections. So this is a very similar structure as to iterating through the load commands, where we just move past each section until we find the Objective-C class list, in which case we can then parse that, which we can see here. Then when we're inside the Objective-C class list, this is like a literal array of Objective-C class objects that the runtime has already populated with the correct data since we're loaded into memory. So because of that, we can actually just use the Objective-C runtime functions on these byte values that we found in this list. There's a million ways you could have done this. You could have parsed the Objective-C class object. You could have done a lot of things. I thought this was the simplest. So we just use class get name and class get superclass to get all of the names of the various classes we're trying to look at. Then we just, return it. And that's basically the entire parsing. Here's a little test framework I made to verify that this worked, and you can see from this you can actually get a decent amount of structural information, but this is a very simple case. Here is the shared with you framework. This is how they do, this is the framework that is used for like screen sharing or the activity controller where you do like the little shared communication stuff. It's not too complicated, it looks like. It just has, a little bit of a radial thing here. Not too many like clusters as you would normally see in an Objective-C stuff. Here is CloudKit. It was a bit too big, but if we zoom in a little bit, we can see right here. That's where all of the database operations are. So you can check this out there. And I wanted to do core data but it got really gnarly. Let's see if I can get this video working. Yeah, it was just, there was too many things in there. But you can even see there's like a guy freaking out in the middle. I think that's NS object. And yeah. But yeah, so that was, the little thing there, just as the example of what you could do with it. I'm sure y'all are more creative than me, so you can figure out other cool stuff. Yeah. So for resources on this, there are the various headers I was referring to throughout: loader, fat, arch, and machine. O'Toole and LiPo are really helpful for working these types of files. And as for books, Jonathan Levin has great books on all of this. In fact, he probably is the person for the definition of he's the documentation for Apple, and he doesn't work there. So Star OS Internals Volume 1 has all of this information and more. So I'd highly recommend it if you're interested in reverse engineering Apple systems. And yeah, any questions or? Yeah.
Are there questions?
Hi, thank you. That was very interesting. Earlier in the talk, you mentioned about Apple code signing some parts of the text section.
Yeah.
And I think maybe I misunderstood you, but you said like it only signs the first part. There was something like that.
So when you code sign to be released on the App Store, or so that your Mac OS app doesn't require them to have to like click through 3 menus to be loaded, it doesn't code sign the entire executable. It only code signs the text segment. So that includes the mock header, and then all your code, and then anything you want to put in there like C strings or whatever. They don't do the entire executable. I'm not exactly sure why, but that's currently how it works. That's also what is encrypted by the iOS store. So you can actually, if you get iOS apps downloaded from the store, there's an old iTunes IT app for Windows that lets you download IPAs from the App Store directly onto a Windows PC. You can actually look at their executables, and you won't see their code because it's encrypted, but that text segment will be code signed and encrypted, but nothing else will. Yeah.
So if I were to rewrite some parts of the Mac OS sections, would I need to re-sign the binary then? Because the signature wouldn't match, right?
Yeah, so if you are using build tooling to do that, you will have to re-sign it. If you're building locally, that's not a huge issue. You can just use the code sign tool on command line. It does get a little more troubling if you're trying to, break into something, right? Because you don't have their certificate. I would say the easiest way to fix that would be to jailbreak the phone you're on, and then you don't have to worry about it. Yeah, that's probably the easiest way to do it. Or there might be a way to do it also using the debugger. However, I don't know the exact way you would do that. I know that Frida is able to get away with breaking code signing using the debugger, so maybe look at the Frida tool, which is also a very great tool for this kind of stuff.
Thank you.
Yeah.
Are there further questions? Okay, that seems not to be the case, and
Sweet.
you now all know how these files work, and have fun with them.
Yeah.
And we thank Garrigan again